This is the second part of the proof of the Cook-Levin theorem. The general idea of the Cook-Levin theorem is that we want to construct a Boolean formula that somehow simulates or captures what the certifier for language in NP does. To make this a bit simpler, we learned about oblivious Turing machines, and we can assume that our certifier is actually an oblivious Turing machine. So now we want to think about how one step of an oblivious Turing machine depends on the previous steps. At step I, we call Si a snapshot of this machine M. And the snapshot consists of two parts. It consists of the internal state of the machine at step I and of the character from the tape alphabet that is read by the machine at this step. So in step I, our head position is somewhere, and that cell contains some character, and that's gamma I. So the snapshot just has two parts. It has the state of the machine at this time and the character that is located under the head at this time. Suppose we know the snapshot at time I. What will the state of the machine be at time I plus 1? Do we know? Yes, the snapshot on time I completely determines the next state that the machine will enter. This is because the next state that the machine will be in is determined by the transition function. And the transition function simply maps the internal state of the machine combined with the character that the machine reads into a new state and then also into a character that is written and a head movement. But I'm only interested in the new state for now. So the state at time I plus 1, let's call it Qi plus 1, depends only on the snapshot at time I, Si. If we know Si, we know what Qi plus 1 is. The second thing we are interested in is how can we find out what gamma I plus 1 is? So what is the next character the machine will read? This is slightly more complicated, and there are sort of two cases. The first case involves the situation where the next character we read was a character that we wrote onto the tape in some previous step. And the second situation is where the next character we read is not something we wrote to the tape in a previous step, but it's part of the initial input. So it was never written by the Turing machine, it was just provided as part of the input. It's the first time we are visiting that particular cell on the tape, and we are just reading whatever character there is provided from the input bits. So it's useful to have some notation to be able to deal with both of those situations. So the first notation we will have is pos of I, which should denote the head position of the Turing machine at step I. Remember that we are dealing with an oblivious Turing machine. So the head position at step I is predetermined. It does not depend on the bits in the input. So pos of I is sort of a constant. It's fixed. The other thing we are interested in is fev of I, which should denote the last time step when the head was at the same position as it is now in step I. And so we are visiting some cell, then we do some other computation, and at a later time we visit that cell again. And then when we visit that cell again, I would like to know what was the previous time that we visited that cell. What was the last time we visited that cell before time I? The reason fev of I is interesting because the character we will read now in this cell, of course, will depend entirely on the character we wrote to that cell the last time we've been there. Right? So last time we've been to the cell, we wrote some character in it, and now in step I, that's the character we will read. The great thing now is that with just this, we know what character gamma I plus 1 is. what character we will read at time I plus 1. If the cell we are visiting at step I plus 1, and remember it's an oblivious Turing machine, so it's predetermined what that cell is. If that cell is visited for the first time, the character we will read is simply the corresponding character from the input. So if the input is the combination of the bit string x and t, we just look at the corresponding position, pos of I, of that input bit string. And whatever is there is exactly what we are reading right now. So whatever is at position I plus 1 of that bit string, of that input bit string, is the character we are reading right now. So that must be equal to gamma I plus 1. However, if we visit that cell not for the first time, then the character we will read now will be the character that we wrote to the tape the last time we visited that cell. And the last time we visited this cell was at pref I plus 1. Again, we're dealing with an oblivious Turing machine, so that time is fixed. It's predetermined. It does not depend on the input bits. And the character we write to the tape at this previous time depend entirely on the snapshot at that time. The reason for this is that the snapshot contains the internal state and the character we read. And the transition function then determines, based on those two things, what character is written. So what character is written at time pref of I plus 1 is completely determined by the snapshot at that time. And so we know that gamma I plus 1 is either determined by the snapshot of pref I plus 1 or of the input bit at position pos I plus 1. So either of those two things. In summary, qi plus 1 is determined entirely by si, and gamma I plus 1 is determined entirely by either s pref of I plus 1 or the input bit at position pos I plus 1. And taking this all together, it means that the snapshot at time I plus 1, si plus 1, somehow depends only on the snapshot at time I, si, the snapshot at time pref of I plus 1, if it's defined, and the input bit at position pos I plus 1. How exactly this dependency is depends on the oblivious Turing machine and the transition function of that machine and so on. But there is some strict dependence on these things. So si plus 1 is completely determined by these three things. So there is some function f that describes the relationship between si plus 1 and these other three quantities. The next thing we observe is that a snapshot can be encoded using a constant number of bits. Say a snapshot can be encoded using C bits. So why is this true? Because the snapshot only contains the internal state of the Turing machine, and the number of internal states is a fixed constant. And the snapshot contains a symbol from the tape alphabet, but the size of the tape alphabet is also a fixed constant. And therefore, the number of possible different snapshots we can have is also just a fixed constant. And therefore, we can encode the snapshot using a constant number of bits. So our function f here, if we look at the arguments of that function, there are two snapshots there and then some bit from the input. And so really there are only 2c plus 1 bits as arguments of this function. And then on the left-hand side we have a snapshot which is also encoded by c bits. So this function f takes as arguments 2c plus 1 bits and maps it to c bits. So we can define a different function g that takes 3 snapshots and a bit and should be true if this snapshot Si plus 1 follows in the correct way from these previous snapshots and the input bit. And so G of Si plus 1, Si as pref I plus 1, and xt pos I plus 1 should be true if and only if Si plus 1 is equal to f of Si s pref I plus 1 and xt pos I plus 1. So this is a simple Boolean function taking 3c plus 1 bits as arguments and then saying true or false. We can encode such a Boolean function using a CNF formula. And the size of this formula will be not too large, by which we mean the size of this formula that captures the behavior of this function g is constant. I will postpone the proof of this claim that we can construct a CNF formula of constant size that captures this Boolean function g to a later video. For now, let us assume this is true. We can now finish our reduction. The basic question we are asking is whether there exists a certificate and a sequence of snapshots encoded as constant length bit strings such that the following is true. The certifier starts with the first snapshot as 1, which should be the starting state and the first character of the input, say x0. Then each following snapshot should follow logically from the previous snapshots and the input. So we should have that Si plus 1 is equal to f of Si as pref I plus 1 and the input bit at the right position, position I plus 1. So each snapshot really follows in the correct way from the previous ones. And then the very last snapshot should be a terminating and accepting end state of the machine. So we had different ways of saying that a machine accepts. Either there's a dedicated state of the machine that the machine will enter to indicate that it terminated and accepts. It would be like something like qaccept. Or the machine just terminates in a universal termination state qend. And then what determines whether the machine accepts or not is the character we read. Both of those things work, but for here, let's just say we enter this state qend, which is a universal terminating end state, and we read 1. So that should mean the machine accepts. So the final snapshot should be a state where the machine stopped its computation and accepts the input. So if we have such strings, a certificate and a sequence of snapshots that end in a terminating end state, then that means that the certifier accepts some certificate T. And that means that the word is in the language. However, if there's no such sequence of snapshots that follow logically from the previous ones and then result in a terminating end state, then the word is not in the language because there's no way to make the certifier accept to make the certifier reach a terminating end state. One thing we still have to think about is how many of those snapshots we need. So how long does it take for us to reach this terminating end state? We know that the certifier machine runs in polynomial time. So there is a polynomial function t such that the machine runs for at most t of n many steps, where n is the size of the input. And therefore, this is how many snapshots we need at most. So this is the idea. We are constructing a Boolean formula that is true if and only if such a sequence of things like the bit string t and then the bit string encoding s1, the bit string encoding s2, and so on, exist. So the only thing the formula needs to encode is all these conditions. So the formula needs to ensure that the first snapshot is really the starting state and the first character of the input, x0. And then the formula needs to ensure that each snapshot follows from the previous ones. We know that there's a relationship here which is captured by this function g, and therefore we can construct a CNF formula of constant size for each of those steps that model the behavior of g. And we finally require that we reach the end state, so we have some brief, short, constant-sized formula that ensures that the final snapshot bit string is actually one that corresponds to an accepting end state. So once again, the first and the last snapshot have to have a specific form that we need to ensure. For both of those, we can construct a CNF formula of size O of C, where C is this constant corresponding to the number of bits we need to encode a snapshot, that ensures that if the formula is true, then the snapshot has the right form. So it's in the starting state and the first character x0, or for the last snapshot, it's in the terminating state and accepts. And then we need further T of n minus 1 CNF formulas, each of which has constant size. Specifically, the size of these is in the order of c times 2 to the power of 2c plus 1. And if c is a constant, that is a constant. We then combine all of these CNF formulas. So all of them have to be 2 at the same time. And in total, we get a formula of size in the order of T of n times c times 2 to the power of 2c plus 1. And this is just in the order of T of n because c is a constant. So this is polynomial in the size of the input. That concludes our proof. We've shown how to construct a Boolean formula given the certifier machine and some input x that has the property that it's satisfiable if and only if there exists a certificate such that the certifier accepts this input x and the certificate. Our construction is not super trivial. I mean, this is a reasonably complex proof. The reason, again, is that the Cook-Levin theorem establishes for the first time that there is a natural NP-complete problem. And so we need to do this much more general master reduction rather than just reducing one specific problem to some other specific problem, which is always easier than these more general master reductions where we do not really know a lot about the problems we are reducing from, apart from just the definition of this complexity class itself.